Hello, good afternoon, everyone. Welcome to Liquid Brain. So today I want to talk about data imputation in R, specifically with the mice package. So there'll be a few chapters in the video where first I'll go through a Google slide on the when, what, and why of imputation, and then we're going to go into RStudio where there will be an R markdown for you to go through some simple imputation such as mean imputation, locf, nocb, and then k nearest neighbor. And then we're going to go into advanced imputation technique with the mice package. Specifically, I'm going to showcase two different types of imputation. In this case, the predictive mean matching, PMM, or we're going to go for random forest, RF. So once we've done that and we compare the performance of these two using a sample data set, we're going to go into a practical where we're going to download the data from the Cancer Genomic Atlas, and we're going to extract the data, do some manipulation on the data, and then we're going to impute the data for the gene expression and evaluate the different performance algorithm that we have for the imputation. So first of all, what is imputation? So imputation is the process of replacing missing value with substitute data. It is usually done as a pre-processing step for downstream analysis where they cannot accept missing value. So when there's data missing in the data set, we do not want to immediately just throw them away because that'll be kind of a waste. So what we're trying to do is to fill in the data based on the trend that we observe, so that even though we have filled in the data ourselves, we have predicted data, it should not change the narrative of the data set or the trend of the data set. So there are a few cases where data can be missing from a data set, where we have missing data completely at random, MCAR, we have missing data at random, and we have non-random missing data. So let's just separate out between random and non-random. So missing data at random will happen in something like a data rot, where some of the data missing from the hard drive. It can happen when you have a paper survey and some rains got in. It can be that some patient forgot to come in for the checkup at a specific day. So some data on that day is missing. While non-random missing data is a little bit more complicated, where a certain group of data is being deleted. For example, you're comparing cancer and normal patients, and all of a sudden, all the cancer patients is missing because it's on a specific thumb drive that you drop into the drain or something like that. In this case, non-random missing data, we can't really impute because it would be really difficult for us to understand what would be the trend in that. But for example, missing at random, missing at random and complete at random will be something like a patient forgot to come in on a single day, where we can try to interpolate the data based on the patient data before and after. So it's a lot easier. So complete at random will be a little bit more random than at random, which is in this case, there'll be it's sort of like there's rain falling on a paper where certain data sets are missing. While missing at random will be something like you run two different analyses on different days, so there's certain gaps within the day where they're missing. But in this case, these two is a lot easier to deal with, but non-random missing data, very, very difficult to impute. So what's the effectiveness of imputation, or how do you measure the performance of imputation? In this case, there's no real answer because there's nothing absolutely universally good about it. Usually if you do interpolation data, it's a lot easier than extrapolation. So in this case, how we're going to measure effectiveness in this video specifically, we're going to artificially remove the data and we'll impute them back. So we can actually compare the original data and the impute data, so we can actually check for the accuracy of data and define that as the effectiveness of the method. So it's a lot more complicated in the real world where you don't understand how it works. So mean matching imputation will be the first imputation method because it will be the easiest, which is fill the NA with means, which is the continuous data, or mode and median for the categorical data. What it does is just fills in the missing data as the mean, so that when you aggregate the data, it doesn't change the mean of the overall aggregation. So it's a simple term, but it's usually not suitable for most situations unless you only consider the mean for next analysis. So for random forest, it will be slightly more advanced, where you try to build a random forest model based on the data set, and then we use the random forest model that we built to actually predict the data that we have. So for example, you can think of it as you're trying to run a linear model, and you have y equals mx plus c line between the two data set, and we can easily use that line, which is that linear regression model, to predict the X from the Y. So same thing, but instead of using a linear model, we're using a random forest model. Everything else is roughly about the same concept. Okay, so the next one is LOCF and nocb, which is the last observation carry forward and next observation carry backward. Sometimes it's actually run as a fallback, where you first run LCF and then you run nocb, so you ensure nothing is missed out. So this is particularly useful for time series data. For example, one of the patients forget to come in for a weekly checkup, so we can actually just bring forward their last checkup data into that day, because most likely between checkup they're not going to differ that much, and you can usually run LCF to actually fill in those data. If you have weather information, for example, one of the day your weather station actually goes out power, so you can also fill in the weather data based on LCF and nocb, and usually it will work, but it depends on the situation, on how large is the time gap between, and do you want to use the mean between the two or moving average. Many things you can choose from. So the next is k nearest neighbor. So k nearest neighbor is actually a clustering algorithm that not usually used as an imputation in the first place, but similar to what we do with the random forest just now. K nearest neighbor builds a model for the clustering process of the dataset, and after that cluster, we can actually check what. Okay, so we're building a k nearest neighbor model based on the non-missing data, right? So after we have done the non-missing data, we can use the non-missing data to predict what is the missing data. So we can do that for every single line. So particularly you only have one column of the data missing, you can easily use k nearest neighbor to predict all of them back. So I'll have a little bit more detail on how you actually run it in R, but basically these are just some information that I found online, which actually helped me a lot to understand how it works. Something like this, right? You can actually just build a model based on the different data set, and then we can actually just, based on what is the dot nearest around them, we can just pull the dot to the 5 nearest neighbor around the missing dot, and we can actually predict the data or impute the data using that. So in mice, in this case, there's a lot of different ways you can do imputation, from predictive mean matching to lasso linear regression to level 1 normal homostochastic PNN or Gimmer mean and all that thing. So there's no correct way to do it. You have to understand, are you imputing a categorical data, numerical data, binary data, and so on. And usually I think what people do is to read some papers and actually run some of the testing to see what happens. So for example, we talked about mean matching just now, but there's actually a more advanced version called predictive mean matching, which actually involves running a linear regression model, predicting a distribution of the missing data. And then from that distribution of missing data, we can actually just pick a few points, and then we use those few points, and when we run the means of that few point to be used as imputation, newly imputed data. So it's a lot more complicated, but in this case, they're of course a lot more accurate and a lot more suitable for most of the data set that you have. So I also have another random forest imputation on how it works. So same thing, it just builds a model and uses it to predict the data set, which is actually very confusing. So the last step of the R script, just to run you through, is we're going to impute the data from TCGA, and which is the Cancer Genomic Atlas program, which has a lot of data from a lot of patients. So it's great for running tests like this where you need a big raw data. So if that's okay, well, let's move on to R, and we can actually start from there. So you can actually download the R script in the video description down below in case that you don't know, and you can actually go there, download, and you can actually continue the video from there. Okay, so once you go to GitHub and download the script and open the RMD file, the script should look somewhat like that. So if you are not familiar with RMD file, everything inside the shaded area is actually the R script, and everything outside is just the text, and they're not actually executable. For example, here I just included the chapter information for what we're going to go through later in the RMD, and you can see some yellow thing that usually the chapter title or the header of a certain section. So we're going to go through what we said just now about mean imputation, LCF, KNN, and we're going to go for the mice imputation with PMM and random forest. And then lastly, we're going to finish off the whole video with the downloading of TCGA data, patient data extraction, inspection, some data manipulation method, and how we're gonna do some advanced imputation, and we're gonna compare the effectiveness of few different imputation method. So let's move on to our first one, mean imputation. So mean imputation is kind of the oldest technique in the world where we just fill in the data with the mean. So for example, we're going to create a very simple vector over here. As you can see, it's 4NA-K7571, and there's NA here and there's NA here. So what we do is we can calculate the mean of the whole thing and fill the NA with the mean. For example, in this case, the mean is 4.75, and after we have filled them in, they're going to be 4.75 here and 4.75 right here. So this is a simple way to do it. You can also do it with the iris data, where it is exactly the same method. You just change the data frame that you have. Just make sure in this case you are using this function, there has to be a single dimensional data. So instead of doing that one by one, we can also write a simple function to do that, and then we can actually run it on, for example, the C++, and we can actually just simplify the whole calculation with a single line over here. So you can see that now what I attempt to do here is to just fill the row 2, 4, 6, 8, 10 with NA, and then input the data in. And again, after I have actually input the data, I print out those data, and you can see now that the data are all 4.873789, which is actually the mean of the whole list of vectors over here. So that's mean imputation. Very straightforward, very easy, but not very useful most of the time because mean doesn't represent a lot of things. For example, let's actually look at the second one just for contrast. So here we're looking for LOCF and nocb, last observation carry forward, and next observation carry backwards. So we're gonna use a package called nocb, which you can actually install the package right here, package install, and just press nocb into the empty slot here, press install, and that will actually load the data into the environment that you're in. So let's first look at LOCF, which is last observation carry forward, and you can see that the 2 now is being carried over to 2NA over here, 3 is being carried over to the next one, and 4 is carried over to the next one, while nocb is exactly the same but opposite, where 1 is carried backwards over here, the 3 is carrying backwards over here, and 4 is carried backwards over here. So of course, it's kind of an issue, so that we usually what we want to run is actually run fallback, which is LOCF and then nocb. So you can see that everything is being carried forward first, and then it's being carried backward again, so that we actually get the first one, but this NA is being eliminated by just carrying backward, so you don't have any trailing MA in front or in the end of the data set. So that's kind of the thing. So we can actually compare the performance of LCS and nocb with this situation right here, where I try to sample 10 data, where I try to randomly select 10 data from a data set. In this case is the air quality data. So what we're gonna do is that we're gonna create a new object called air quality missing, and we're going to remove randomly 10 different data set in this temperature situation and fill with NA, and we're going to use a fallback to actually impute the data in. So the next one we're going to do is actually just extract out the missing data as original data and imputed data. So the original data is the one before we fill it in with NA. So that's the original data, and this is the one after we have imputed in. So after we compare them to numeric, we can just plot them out and actually just plot them out again just to see. So as you can see that the original data and the imputed data in the real perfect scenario should be exactly the same. So that should actually line on this line over here. But as you can see, sometimes they're not, the fallback algorithm doesn't perform that well all the time, but in this case, they're kind of good enough. As you can see, this is the original data set, and this is the imputed data set. You can see that even though some of the data are quite different from one another, right, as you can see here, the data still falls within the trend of the data, and I don't think it will be causing a problem for a downstream analysis. For example, if you're running an RNN for the next step, for example. Of course, I will use something like a moving average, but fallback in this case, LCF kind of makes sense for this case. But of course, run it on your own and see how it performs. There's no correct answer to how to do things here. So the next one is actually just K and N, how it works, and then how K and N imputation actually works. So we're going to run through KNN situation first, and then use that. We should be able to understand how KNN imputation works because it's a single line of imputation again. So first of all is we're going to use iris as our, what is that called, a sample data set. We're going to create a data frame called df, which is actually the same as iris. We're going to create a min-max normalization function, which takes the largest number and then put it as 1, smallest number and put it at 0. And we're going to actually just apply to the column 1, 2, 3, 4 over here. And we're going to have a new object called df norm, which now will only have 4 different columns with the petal and sepal length and width. And we have the largest as 1, lowest as 0. So it's actually min-max normalized. So once we're done that, we can actually just run a sample thing to actually select some of the training set and the testing set. Things like, so remember, we're not running imputation here, we're running a clustering algorithm. So what it does is that it should be able to use KNN to actually predict the testing set based on the training set data. Right, so we're going to use a can of 30, which is a little bit too much, but let's actually just run it to 3 because we know there's 3 species over here. So as you can see that the training accuracy on KNN is actually pretty good, means that we can actually predict the species almost like 98% accuracy or something like that with the KNN model that we have. Remember, KNN here is a classification model, so we can actually, based on the training set, we train a model and we use the model to predict our testing set. And in this case, our accuracy are pretty high, just to based on their petal and sepal length, we're going to predict their, what is that called, the species. Okay, so what we do later is, again, we're going to write an accuracy function, and we can see that our model has 93% accuracy. And that's what we want. Remember, when you are running a clustering or modeling algorithm, we do not want to run it as 100% accuracy. That is going to be a problem because it's going to be a lot overfitting situation here. So what happens here are very similar, where we are using KNN imputation, but they're not going to be as transparent on how we run it just now. So what we do is, again, here we're going to do the same thing where we try to do a df missing on the sepal length. As you can see here, some of the sepal length is missing. So once we're done missing, the way to run KNN imputation is just literally a single line. And what they'll do is that they'll try to use the data from the other 3 columns, and we try to build a model on the other 3 columns, and then we rebuild the data back on the first column on the sepal length. So that's basically the concept. And then the rest are kind of just a performance evaluation of how it works. Actually, let's just run it and see what happens. And you can see that using KNN imputation, the original data and imputed data are pretty close together. We can't actually tell too much of a difference. But if you do want to see the percentage difference between each other, some of them are actually pretty big, which means that KNN might not be the best situation here to actually try to impute the data. That might not work as well. So I actually again also try to do a little bit more jingling in the number of neighbors that I have in this case. So we can see that on most of the neighbors, I think they perform pretty similar. I would say the best is maybe about 3 different neighbors, where, because we know there's 3 species, and you can see that the imputation results are pretty balanced from positive and negative. While if you have 1, then negative is very strong. While you have 10, actually 10 and 3 is very similar to each other. So yeah, it depends on how you want to define the accuracy and you have. But for in this case, I might not want to use KNN to actually try to impute the data if I'm dealing with sepal and petal length, for example. So that concludes our simple imputation with mean, with locf, nocb, and KNN. So now we're going to go into a library called mice, which actually I forget the full name about, but it means like something missing data or whatever. I'll put it right here over there. So we're going to run to how it's actually being run first, but we're going to not go too deep into algorithm, but more on the execution and practical about how it is run. So in this case, the actual way to run it is just one single line, but let's go from the beginning. So first of all, we're going to create a data with the sample data set, which is air quality, and we're going to fill the first 7 data of column 3 as NA, and the first 5 data as column 4 as NA. So you can see the first 7 of them. So in column 3, there's some sample data, and as column 4, there's some missing temperature data. There's also some missing data that's originally coming from data set. We're not gonna look at them, but just be in mind that they are there. Okay, so the way to do it is just run it, and the only thing that you kind of need to know here is the m equals to 3, which that will give you 3 sets of predicted data, and we're going to actually use that 3 set to recombine them into one, which is actually using the complete command over here. So in this case, we can take a look at the temporary data, which actually has a lot of things, because this is the original input data and this is the input data, and it's kind of long, so I'm not gonna go through too deep with it. But what you need to know is every single missing data over here is being imputed with 3 different values. So once we're done the 3 different values, right, you can actually see that these are all the information that we have with the imputation technique that they use. And why do months and days that imputation technique? Because there's no missing data, right? Okay, so these are the predictor matrix of what they are using. And so how do you actually, in the end, combine the data back is to use the complete function, and your input data should be right here. Yeah. So as you can see, the first 7 data from column 3 has been now filled in, and the first 5 data from column 4 has now been filled in as well, together with all the ozone and solar and all the situation over here. So how do we actually compute the difference? First of all, I don't like to trust a single number. So this is actually the raw number between column 1 and 2. So column 1 is the original data from the air quality before we actually remove them. And the second is the input data that are imputed using the PMM predicted mean matching method. As you can see that they are close enough, but that column 3 might not be that suitable. They're quite different. These are good enough. So they're quite close, right? So actually now also let's look at column 4, which is the temperature. Remember, temperature here is Fahrenheit, which is why it's so high. But yeah, column 4 might be a little bit of an issue over here, where the predicted number is not actually that similar with the original number. So it might be due to the concept that there are other column missing as well, because we only have, in this case, 6 different data, I think. Not here. Imputed data. Yeah, I don't know where is it. What did I call it just now? Temp data. Oh, it's just called data. So we also have very little number of data to predict. So column 4, yeah, it might. So column 5, I expect it will be a problem, because it cannot use ozone and solar radiation to predict our wind and temperature. So I predict column 5 is going to be slightly bigger, and column 5 is going to be slightly bigger, which is kind of true, but not really in some cases. So that's basically the predictive mean matching, and how they actually create the thing, and then they create everything in the background, magic happens, and you get imputed data, and this is the performance. So the great thing about mice is doesn't actually just need to be running on a mean matching. Actually, they have a large range of different things you can run. For example, the method now I'm using is called a random forest, which we're now gonna do exactly the same thing. We're gonna have 3 sets of data being imputed, and we're gonna join the 3 sets of data into one with the complete function again. And beware that if you have a big data set, this is gonna take quite a while. So if you're running on 10,000 genes, it's gonna take like an hour or 2, I don't know, depends on the computing speed. And we're gonna do the same thing, but now instead of actually just to look at raw data like we did just now with PMM, we're actually gonna plot the performance out between two of our imputing algorithm. So for example, the PMM is gonna be the red color. Sorry, the original is gonna be a blue color. So remember, blue color here is the original data from column 3 and column 4. The red color is gonna be the predictive mean matching PMM, the red color, and the green one is supposed to be the RF. So you can see that they are, in terms of the column 3, they are actually not that far away. The green one has a big spike over here. So the red overall perform better when the number is lower. And when the number goes higher, I would say the red ones still perform better in terms of they're closer to the trend of the whole thing. But the green one is kind of reversing the trend of how the whole thing to run. But both of them doesn't perform absolutely well, because there might not just be enough data from the other column to actually do the prediction in the first place. But this is a way of how we can compare if the imputation algorithm actually works or not. So now, using the same concept, we can actually move on to our TCGA and then actually use the same concept and same mechanism to run an imputation on the gene expression. Okay, so once we have figured out that, let's actually move on to our TCGA data, specifically how to download them and actually simulate a situation where there's missing data, impute that in, and measure the performance. So how do you download TCGA data is using the TCGA bio link, and these are the exact code that you can use to run it. So I'm actually targeting the gene expression data, which is why I'm using the transcriptome profiling, gene expression quantitation, and RNA sequencing. So I'm also actually subsetting a barcode over here because I want enough column for me to do the imputation later, but I also don't want it to be too big so that it runs out of RAM to run it, or it takes way too long to run it. Okay, so once you're done, just run a query, run the download, run the prepare, and actually you get a summarized experiment data set. So I'm not going to do that. I'm just going to load it directly from my RDS because I've done it earlier, and GDC prepare takes quite a while to run. So don't get surprised if it actually appears to be freezing out. So once you're done that, TCGA data has a few things. If you're not familiar with the summarized experiment object, you have row ranges, which contain all the information about the gene. Column data contains all the information about the patient, their age, the treatment, and all the other mutations do they have. And the assay is the one that we look for, which contains all the gene expression data. Okay, so once we've done that, we're going to extract the gene expression data over here. We're going to use the TPM on strand. So that should actually give us the raw data over here. So of course, there'll be 60,000 over 36 different variables, which is a lot. So we're going to do the first thing first is actually we don't need to remove them anymore because just now there's some extra column. But the first thing we're going to do is actually run a log 10 of it, because if they don't run a log 10, gene expression data is very left skewed and negatively skewed, and we can't actually, the algorithm has a hard time to try to figure them out. So next one we actually try to remove is the low count. So I'm going to use a cutoff of 1 just to limit the number of things that we have. But in this case, number of 1 doesn't seem to work since I still have 60,000 of them. I'm going to use 10. Still doesn't work. Oops, nope, this is the one. Okay, so I'm going to remove from just now how many? From 60,000 now to 18,000 of them. So I can remove all the data with the low count rate. And then I'm going to only select the first 1,000 of them. Why I did that is because I'm making a video and I don't have enough time to actually show you how to run 10,000 of them. You can if you're running a research, definitely include all of them for your imputation. And because I don't know what is the effect of selecting 1,000, but I can't wait 2 hours for the run of the imputation. Okay, so what I'm going to do next is actually select 20% of the sample using the sample functions over here. I'm going to select 20% of the data over here, and we're going to fill in them with an NA. So you can look at it so between the raw data and the missing data, raw data have all the data, or missing data has 20% missing data on the first column. So why I did it on the first column just to make things easy, but remember the imputation that we did with the air quality we did just now, you can actually run it on all the different columns and it will actually impute all of them. Just make sure that you don't have like row 1 to 8 has all the missing columns or all the missing rows, and then you will have a hard time trying to impute the data in. But if you only have a single column missing, it's usually easier for them to run. Okay, so the first imputation method I'm going to use is the random forest, because obviously it's done very well just now comparing PNN and random forest. So I'm going to do that, and again, this is going to take like some time, so don't get too surprised if it actually takes a long time to run, especially if you're using a lot of different genes, for example. So there's number of logger events 150, because in mice there will actually be some output that I actually suppress with the print flag. But just don't get too surprised. Don't get too worried if this happens. And the next one, I'm going to run something different. It's called Lazo Select Jet plus linear regression, which I feel like it's going to run better on my gene expression data. But because of the way I subset, I actually cannot be too confident that it will, because I might have actually killed the trend by selecting 1,000 out of 18,000. But that's one of the algorithm that you can use, because I remember that the elastic net is actually used, elastic net regularization is actually used a lot for gene normalization and gene expression normalization. So this is what I want to try. So the last one is actually just similar to what I did above with the visualization of the performance. So what I do now is to try to plot them out. As you can see that again, blue color is the original. So the red color is the first imputation method, in this case random forest. The second one is the green color, which is the log normal. Is it log normal? No, the log select plus linear regression model. But the problem is they're all overlapping together, so it's really hard to tell. But I can already tell they work quite well. Actually, am I running all of them? Yeah. So remember, so this is only the 20% of data that's missing. None of the data here is actually from the original of them. So no, actually there's 1,000 of them. Sorry. Yeah, my fault here. This is all the data, but you can see that I can't really tell the imputed data from the original. So the imputation sort of work. But of course, we don't want that. So what we do is we want to actually ensure that we want to also cross-compare the performance of the algorithm based on the size of the count, because obviously if the count size is big, the imputation has more thing to play around. So what I actually do here is trying to calculate a percentage error of each of the imputed data right here. Okay, so p data, I remember I did actually run it to here. Original imputed, this is the length. Imputed, yeah, this is no. Yeah, this is basically 1,000 different, 1,000 line that we included in the overall. So once we actually, so this is what we call residual plot, where we calculate the percentage differences on each of the imputed data against the original. So if it's larger count, if it's 100 away, 200 away, not big of a difference. But if it's 10 and it's 100 away, it's going to be a huge difference. So after done that, I can just plot 2-line plot. But now remember the x scale, sorry, the x-axis here is the count number, which is the size number of the original count rate, and the 2 lines, red representing the random forest and the green representing the lasso select plus linear regression. And we're gonna actually scale the x as a log 10. So remember that the x-axis here is a log 10 scale. And you can actually see on the plot that the green color, the lasso select here, actually works much better than our what is that called, our random forest, which is kind of what I anticipated. And you can see that everything with a low count rate over here, we have a huge difference between the original, because remember, if there's no difference from original, it should be on 0, but there'll be some variation up and down over. So I'm glad that both algorithms shows kind of a balanced profile. They don't go up all the way, they don't go down all the way, so they kind of work okay. But the green one just follow much closer compared to the red one, except for one big spike over here. But overall, I'm happy with the result. And if I were to actually impute gene expression data, I might actually go for the log select plus linear regression. So that's basically what I want to say for the imputation today. So I'm glad it actually works out okay. And I hope you learned something today about imputation. Definitely do say subscribe, and I'm going to have a lot more video like this coming up next time. That's all. Bye.